Hemlock, Compact and Scalable Mutual Exclusion. My name is Dave Dice, and this is joint work with my colleague Alex Kogan. We're both in Oracle Labs based in Burlington, Massachusetts. We'll briefly cover some background material on queue-based locks, of which Hemlock is an example. Then we'll cover the Hemlock algorithm itself and its performance, and finally close with discussion of some advantages and disadvantages of Hemlock. The key queue-based locks are CLH, Craig Landine Haggerston, and MCS, Mellor Crummy Scott. These have been the gold standard for queue-based spin locks since about 1991. MCS is used in the Linux kernel, for example, as the lowest level mutex construct in the system. Both of these locks are FIFO fair. They show excellent scalability under contention, and they have reasonable latency for uncontended operation. For our purposes today, we'll focus on MCS for comparison. In MCS, a lock consists of a single word. That word points to the tail of a queue, and the elements in the queue are queue elements, which we'll describe momentarily. We use an atomic swap operation to append queue elements to the tail of a linked list. The swap operation in queues and returns the address of the immediate predecessor queue element. The head of the queue is implicit, and that's the owner, and we use local spinning on a flag in the queue element. That's actually critical to the performance of these locks. At most, one thread busy waits on a given location at any one time. This allows faster transfer of ownership because when we actually perform the store that conveys ownership, we need to only invalidate one cache. Queue elements can be associated with at most one lock and one thread at any one time. It's useful to look at MCS in action. On this slide, we're looking at an example of a lock that is in the unlocked state. We'll designate our lock L1 and notice that its tail pointer is null or 0, indicating that the lock is not held. Next, let's say a thread tries to acquire lock L1. The thread first prepares a queue element, E1, and then uses the atomic swap operation to install the address of E1 into L1's tail pointer. The return value from that swap operation, the previous value of the tail pointer, was null. Therefore, we've acquired without contention, and the thread has immediately gained ownership of the lock without any need to wait. The queue element has two fields, a backlink field and a busy wait field. Neither of those fields are used in this case because we have an uncontended acquisition. Next, let's say another thread arrives to acquire L1. That thread posts the queue element E2 to the tail of the queue. In this case, the return address from the swap operation is E1. That's non-null. Therefore, the thread knows it needs to wait. In this case, the thread that posted E2 then proceeds to set E1's backlink to point to E2, forming the queue, and also then starts to busy wait on the flag inside E2, the element that it posted. Then another thread arrives and posts the queue element E3 to the tail of the queue. In this case, the return value from the swap operation is E2. The thread that appended E3 then updates E2's backlink to point to E3 and then proceeds to busy wait on the flag inside E3. The current owner is the thread that posted E1. That thread then proceeds to unlock L1. In this case, that thread follows E1's backlink to reach E2. It then sets the busy waiting flag in E2 to convey ownership to the thread that posted E2, and then finally reclaims E1. The thread that posted E2 notices the change to its busy waiting flag from 0 to 1. That indicates that it is now the owner and it can enter the critical section. Queue elements have a life cycle and require allocation and deallocation. In some cases, if we have strictly balanced locking, we can allocate the queue elements on stack. In the common case, though, locking APIs don't require such balance, and therefore we can't allocate queue elements on stack. For instance, the pthreads interface and the Linux kernel locking interface does not require balance. The typical solution in that case is to use a per-thread cache of available elements, and those elements will have originally been acquired through malloc and free operations. MCS imposes an additional constraint that we pass the address of the queue element posted from the lock operation to the corresponding unlock operation. So why is that? Well, in the case of contended succession, we need to reach the successor's Q element and set the flag in that element. In any case, contended or uncontended, we need to reclaim the element. In particular for MCS, when a thread posts an element to the queue, at unlock time, it reclaims that same element. So, how would we do this? Well, we could use a non-standard API to pass the queue element address from the lock operation to the unlock. We could also use the thread local map that maps the lock address to the queue element. The most common way, however, is to add another pointer into the lock body. This points to the head, the owner queue element. And this is protected by the lock itself. This sounds awkward, and it is. And it increases the lock size. We add an extra field to point to the head. It increases the path length, and it increases coherence traffic. But it's simple. Illustrating that idea, we add another field to L1, the pointer to the head, which maps all the way to the head to E1. So in this case, the lock now contains two pointers, a pointer to the tail, where threads append themselves, and a pointer to the head, which is the owner. And obviously, when a new thread takes control and takes ownership, it needs to update the head pointer. We'll briefly contrast MCS and CLH. Under CLH, threads busy wait on a field in their successor's queue element instead of the element that they originally posted to the queue. Waiting threads know only the address of the predecessor element. That is the address returned from the atomic swap operation. In fact, a thread knows only the identity or address of its immediate predecessor in the queue and does not know its successor. It's also the case that the unlock operator in CLH is wait-free, and the paths are somewhat shorter than what we find in MCS. CLH, however, requires that we pre-populate locks with so-called dummy queue elements. This impacts adoption because of space concerns. It also means we require explicit lock destruction to reclaim those dummy queue elements. In CLH, elements circulate or migrate between threads. So when a thread posts a certain element to a queue, when it reclaims an element, it may get a different one back. That means there's no chance of on-stack allocation for queue elements. We'll now shift to Hemlock. Hemlock is in the same family as MCS and CLH, and in fact, it's inspired by both those locks. Similar to the MCS and CLH, arriving threads in queue with a swap operation. In Hemlock, each thread has a private singleton grant field. The grant field resides typically in thread local storage, although other options are available too. Threads install the address of that field into the lock's tail pointer with the atomic swap operation. And the grant field acts as a mailbox between threads and their immediate successors in the queues. The key to Hemlock is that there are no queue elements. In Hemlock, when a thread needs to wait for the lock, it busy waits for the address of the lock to appear in its predecessor's grant field. And particularly, we have address space notification for transfer of ownership. And recall that the address of the predecessor was obtained from the atomic swap operation that the thread used when it enqueued originally. Once a thread has obtained ownership, the recipient then clears the grant field in its predecessor to acknowledge transfer of ownership. This allows reuse of the grant field and allows us to use a single one per thread. Threads in unlock wait for the successor to reset its grant field to 0. This represents an additional interlock or delay between the thread in the unlock path and its successor. That sounds like a bad thing, but I'd point out that waiting is outside the critical path and does not impinge on scalability. So, Hemlock avoids queue element lifecycle issues by virtue of the fact that it doesn't use queue elements. It's also context-free in the sense that there is no information that needs to be passed from the lock operation to the corresponding unlock operation, as there is with MCS and CLH. This further simplifies the implementation. Now we'll take a look at Hemlock in action, and we'll examine the unlocked state. In this case, we have lock L1. It has a tail pointer field, and that's 0 or null, indicating the lock is not held. Say thread T1 now arrives to acquire L1. T1 swaps the address of its grant field into L1's tail pointer. The tail pointer now points to T1's grant field. In this case, the return value from the atomic swap operation was 0. Therefore, T1 acquired the lock without contention, without a need to wait, and it can immediately enter the critical section. Thread T2 now arrives and attempts to acquire lock L1. T2 enqueues itself in the usual fashion using an atomic swap operation to install the address of its grant field into L1's tail pointer. The value returned by that atomic swap operation refers to T1's grant field. Since that value is non-null, T2 knows it must wait. T2 then proceeds to busy wait on the location, the value inside T1's grant field. It's worth pointing out that this is similar in a sense to how CLH busy waits. In CLH, threads wait on a location associated with the predecessor. And similarly, thread T3 arrives to try to acquire lock L1. And T3, again, appends itself to the tail of the queue. In this case, T3 waits on the value inside T2's grant field. T2 waits on the value inside T1's grant field. And T1 is the current owner of the lock L1. It's worth pointing out that T3 knows the identity of its predecessor in the queue, T2, and T2 knows the identity of its predecessor in the queue, that being T1. Those values were returned by their respective swap operations. However, T1 does not know the identity of its successor, T2, and T2 does not know the identity of its successor, T3. Next in our scenario, thread T1 unlocks lock L1. T1 writes the address of L1 into its own grant field. T2 observes the update, that is, the value of L1 in T1's grant field. T2 then resets that grant field in T1 back to 0. T1 sees its grant field restored, returns from unlock, and T2 now enters the critical section. T2 is now the owner of the lock L1, and T3 busy waits on T2's grant field. We'll now set up an entirely new scenario that illustrates a phenomenon we call multi-waiting. In this case, thread T1 holds locks L1 and L2. There are no waiting threads. L1's tail pointer points to T1's grant field, as does L2's tail pointer. Thread T2 now enqueues on L1 and waits, and T3 enqueues on L2 and waits. T2 busy waits on T1's grant field, and T3 also busy waits on T1's grant field. We now have a scenario we call multi-waiting. With multi-waiting, we've lost the desirable local spinning property where at most one thread busy waits on a given location at one time. Next, thread T1 releases lock L1, and it does so by storing L1 into its own grant field. Both T2 and T3 monitor or busy wait on T1's grant field. T1 has written the address L1 into its own grant field. T2 observes that update, which indicates T1 has transferred ownership to T2. T3 also observes the update and observes the value L1 in T1's grant field. But as T3 is waiting on lock L2, it ignores that update. T2 then stores 0 into T1's grant field, overwriting the value L1, which was previously there. This, in a sense, resets the mailbox, making it empty. T2 then enters the critical section protected by L1. At this point, T2 holds lock L1. T1 still holds L2, and T3 waits on T1. Multi-waiting results in non-local spinning and potential performance loss. Specifically, we have write invalidation into multiple caches, which can slow the propagation of stores. Notice that Hemlock writes the address of the lock into the grant field to disambiguate against potential multiple waiters. Hemlock does provide local spinning absent multi-waiting, however. So how frequent is multi-waiting? We believe it to be rare based on our own empirical analysis. There's also the literature on lock set size analysis and static race detection also just suggests that many applications hold just one lock at a time. Thus, there's no possibility of no multi-waiting. We'll now compare the memory usage requirements for MCS, CLH, and Hemlock. In the following table, the symbol E represents the size of a queue element. For MCS, each extant lock requires 2 words, one for the head and one for the tail. Each held lock requires 1 queue element. So if a thread holds 8 locks, it'll have to have 8 queue elements in play. And when we're waiting on a lock, it requires an additional queue element. Per thread costs are technically 0, but in practice most implementations have per thread lists of free elements. CLH requires the dummy node to be present. So each extant lock requires two fields, the head and the tail pointer, and population with the dummy element. So it's 2 plus E. Each held lock requires an additional 0 cost in memory, and each waited upon lock costs an additional Q element. Similar to MCS, in theory, the per thread cost is 0, but in practice, again, we have per thread. We usually find per thread free lists. Hemlock is quite different. Each extant lock requires only one pointer to the tail only. Each held lock has a 0 cost. Each waited upon lock has a 0 cost in memory. And per thread, we have one field, that being the grant field. We'll now introduce an optional optimization we call CTR, or Coherence Traffic Reduction Optimization. This relates to the busy waiting policy, where a thread waits for the address of a lock, the lock of interest, to appear in its predecessor's grant field, and then resets that grant field to 0. Notice that we have a very rapid back and forth communication pattern on one location. We'll assume momentarily that we have a simplistic, MESI, modified, exclusive, shared, invalid cache protocol. The thread busy waiting waits in shared state, in S state, and it waits for the address to appear of interest to appear in the predecessor's grant field. At some point, the predecessor writes the value of interest into the grant field. Therefore, it invalidates the outgoing thread, invalidates the line from the waiting thread. Then, the waiting thread pulls the line back in with a cache miss to restore the line into S state to observe the changed value. Then finally, we reset the value to 0. So we have to upgrade the line from shared state to modified. As you can see, this is a fairly busy, lots of coherence, traffic, and activities in this protocol. With CTR, we busy wait with atomic operations to avoid that final upgrade from shared to modified state. That is, instead of using classic loads to wait for the value to change and then a store to reset it, we busy wait with atomics. Normally, such a policy is an anti-pattern, but it's acceptable for this very specific point-to-point communication mode. CTR provides benefit on AMD and x86 systems, and we've actually tested and shown this on a wide variety of systems. Systems that use the newer UPI coherence fabric and the older QPI fabric, old and new models, and on NUMA and single-node systems. We also use a variation of CTR on Spark, but Spark has a more efficient mechanism to wait for cache line invalidation. We'll now show some performance results. We used the LevelDB read random benchmark, which tests the scalability of random reads against a database. All our locks were implemented in an LD preload interposition library. This allows us to change the lock implementation without it changing the application proper. And the application uses the standard POSIX pthread mutex API. On the x-axis, we have the number of threads, and on the y-axis is aggregate throughput. We used a 2-node x86 system. The system has 2 nodes, 18 cores per node, and 2 logical CPUs per core, for a total of 72 logical CPUs. As we can see, Hemlock does relatively well compared to CLH and MCS. This graph also includes data on a classic ticket lock implementation. Ticket locks traditionally perform very well at low levels of contention, but then fail to scale under higher load. As we can see here, this is the case. They fail to scale because they do not provide local spinning. So, what are the disadvantages to Hemlock? First and foremost, it admits multi-waiting, which we believe to be rare, but if multi-waiting does occur, then we have high remote reference complexity, which is undesirable and impinges on performance. Another question is the CTR optimization. Is it portable or platform specific? We also have waiting in the unlock operator. In Hemlock, a thread that's released a lock always waits for the successor to clear its grant field. In MCS, a thread in unlock may need to wait for the successor to fill in the backlink. In CLH, in contrast, never waits. It has a strictly wait-free unlock operator. We'll now switch to the advantages enjoyed by Hemlock. Hemlock avoids queue elements and therefore queue element deallocation, allocation, and lifecycle concerns. The API for Hemlock is context-free. We don't need to pass any information from the lock operation to the corresponding unlock. Hemlock's simple. The paths are extremely short. Hemlock has low latency and high scalability in common scenarios. It's easy to implement and integrate as a replacement for other locks. has extremely parsimonious memory usage. It usually enjoys local spinning, absent multi-weighting, and like MCS and CLH, it's FIFO. You can find an extended version of the SPAA paper in arXiv. The arXiv form contains data on additional experiments. For instance, we looked at the CTR optimization and how much it contributes to performance. We also set up intentional multi-weighting scenarios to see actually how badly Hemlock will do in unfavorable circumstances. And finally, we describe additional variations and optimizations. Thank you for your time, and feel free to contact me if you have any questions.